First of all, do you guys hear me? Is the volume okay? Thumbs up, sounds good. So today's talk is going to be about Pwning, Adobe Reader, with its embedded XFA engine. So first of all, sorry for the delay. My laptop only supports an ancient technology which is called VGA and not HDMI. That was the reason for it. So on the menu, we have first of all a short who am I. Then I'll switch over to explaining the motivation behind this talk, and we'll have a short introduction to XFA. This one is going to be really short because afterwards we're coming to the meat of this talk, which is going to cover the XFA internals, especially the XFA objects and the JF Cache Manager, which is a custom allocator in Adobe Reader. And afterwards we'll switch over to the exploitation part. And today we also have a demo, a zero-day demo, and a conclusion and Q&A, of course. So short, who am I? I'm Sebastian. I'm co-founder of a small IT security consultancy in Germany called Sebastian. Was founded in 2009. We're mainly doing the typical IT security consulting stuff, like pen testing, code audits, and so on. But we're trying to do as much as possible in the research field because that's where the fun is at, right? I mean, auditing PHP web applications is also nice, but digging into huge binaries, finding vulnerabilities, exploiting them, that is a lot more interesting. So that's what we try to concentrate more and more on. I would myself describe as a low-level addict. I just love reverse engineering, bug hunting, exploiting stuff, looking at complex technology, trying to break it. And yeah, in the past I've found a couple of vulnerabilities and succeeded in Pwning in 2014. So about the motivation behind this talk. In 2015 we did an extensive fuzzing run at Sebastian, and the goal of it was actually to take part in Pwning 2016. But as you might have noticed, Reader was not among the targets this year, so bad for us. But what we had was a huge database of crashes. We had like, I don't know, 10,000 crashes or so. And we had a pretty hard time doing an analysis on those crashes because the amount was just so huge. And the analysis for those cases was also pretty hard. And by showing you a typical Reader vulnerability, a typical crash, I want to explain why this is hard to analyze. So that's a typical crash, awesome. EAX references some memory address somewhere which is not mapped. But if you have a look at it, the function name does not really tell us much. It is DLL unregistered server with a huge offset, so that doesn't look too good for us. And if you trace a little bit backwards and you see that in ECX you have the object which references or which carries the bad reference. And if you do a bang heap on it, that's what you usually do if you have a vulnerability and you want to start digging into it and the root cause. You would check it out with page heap and you see, oh, ECX is somewhere located in the middle of a huge chunk of size CCD8. So that doesn't look too good for us either. So page heap in that sense is totally useless. And if you do a stack trace, you don't see much more info. You always see those DLL unregistered server functions, so you can't actually use it. What we have is Adobe Reader has no symbols, obviously, and they even strip the RTTI infos, some version 10.x. So we don't have function names, we don't have any object vtable information. We can forget about the stack traces. Page heap is obviously also useless, and that is quite a pain because root cause analysis is pretty hard with that. And it also complicates crash triaging during fuzz runs if you want to say, okay, is this a new vulnerability? Is it unique? Is it maybe exploitable? All that kind of stuff gets really hard if you don't have any contextual information. So the question is, how do we analyze those crashes? And of course, as well, how do we exploit them? And it's obvious we need context somehow, and we need symbols. If you look in the past, what research has been done in the XFA field, we don't find really much. What we do find is write-ups, log entries about this XFA exploit, which surfaced in 2013. It has been analyzed by David and Enrique of Immunity Inc., and as well by Mathieu Bonetti of Portcullis Labs. They did really thorough analysis of the exploit itself and how it works, but they don't go deeper into it, and they don't really do in-depth research in the XFA field. So what I want to do when I started with the whole topic was write tools to recover contextual information, and to make it easier for you guys as well to have a look at Adobe Reader and maybe write an exploit for it. I will release some either Python scripts and some other tools which are going to be published on our GitHub during the next days. I'll try to publish them at the beginning of next week. And what I wanted to do with this is I wanted to facilitate vulnerability discovery, root cause analysis, and the crash triaging process during the fuzz runs. And of course, deliver some XFA-specific background when it comes to exploiting Reader. So much as to the motivation behind this talk. Let's have a short look at what XFA is actually all about. So XFA is the XML forms architecture. You always have it when you open a form, then it is that you can fill out, then it's very likely that XFA is behind it. It's a specification, it's not a standard, and the specification is huge. It has nearly 1,600 pages, so it's not an easy evening read. It's very complex, very long, and this is of course nice for us. We all love long and complex specifications. And what XFA generally does, it brings dynamic behavior to the otherwise static PDF world. So these forms can change their layouts. Maybe you've seen tables that you fill out and you click a button and the table expands. That is typical XFA behavior. And the dynamic part behind all this is driven by SpiderMonkey. SpiderMonkey 24 in the case of Acrobat Reader DC. And XFA is not supported yet by many PDF readers. You actually only have the Acrobat products, of course, and Foxit Reader obviously supports it, and I think Phantom PDF or what it's called. But other important PDF readers like Chrome, Chromium, Firefox, so the Windows embedded PDF reader, they do not support XFA yet. Maybe soon. Let's see. So the XFA form data itself, it is an XML structure which is embedded in the PDF, and it is a so-called XDP packet. And if you also have JavaScript in your XFA form, it is also embedded in this XDP XML chunk. And JavaScript is always executed upon certain events, like for example the PDF is fully loaded, or you click a button, something like that, then JavaScript is being executed. So let's have a look at a practical example. That is our XML chunk. I hope you can read it. It always starts off with the root tag XDP, and it is followed by a certain number of DOMs. It always starts off actually with the config DOM, which are certain configuration objects for XFA processing. And the most important DOM is the template DOM. It actually contains all the important objects which are later displayed to the user, like a table, the buttons, stuff like that. And in the template as well, you can find the event objects that define your JavaScript actions when you do something. In this case, we have an event handler for the event click. So if you click the button, app alert 1337 pops up. So these two DOMs that we've just seen are not the only ones. There are many more, and the amount of DOMs and objects which are under these DOMs is really, really huge. So in total we have far over 200 objects that are accessible via JavaScript. And of course all their methods, all their properties that you can set and get. It's really crazy, it's a huge attack surface, and that's something I just wanted to show you. All the other DOMs that we have here, datasets, form, layer, XCC. This defines the whole attack surface for XFA, which is just immense. And I'm pretty sure that if you guys fire up a fuzzer for XFA, you'll also drown in vulnerabilities. It's really amazing how much functionality is behind it. So let's dive into the XFA terms. So my general approach was kicked off actually by a tweet by Niels, who tweeted to Frege, hey, I found a Solaris version of Reader, and it seems to have symbols, and the allocator that you're talking about is the JF Cache Manager. And I was like, okay, we have a Solaris version which contains symbols. That is very interesting. I was immediately looking for the newest version of Reader that had symbols available, and I found version 9.4.1, the Solaris version, which still had symbols available. After that, they were gone. So I thought, why not try to somehow port the symbols within this old acroform.api module, which is the module which implements XFA, to a newer version of Acrobat Reader or Adobe. I stumbled over some problems. For example, the code is rather old. It's from 2012, but the point is that we have many code changes between version 9 and Acrobat Reader DC. So if you just have a look at the function count, in the Solaris version you have 48,000 functions, and in DC you have 95,000 functions, so they even nearly doubled the amount of functions in it. And something that you immediately think of, well, if you have a binary with symbols and another binary without symbols, you try to match it somehow, maybe using diaphora or bindiff or whatever you prefer as a diffing tool. I tried to do it with diaphora, but that was not the way to go, because it's a different platform, it's a different compiler, and the functions just differ too much. For example, the Solaris version uses heavy inlining, and that screws up the matching heuristics of diaphora. I was talking to Ossian at Syscan this year, and he said that this is one of the key issues that he's working on right now. So he's always improving his tool. It's really awesome. I love diaphora, but just in this case, it was not ready to tackle this problem. So another problem I stumbled over was that structures, object, and v-table sizes differ. Only slightly, but it's enough to totally screw up your heuristics, and you can't really use it to match functions. So that was all not too positive for me. So I tried another approach. I was like, okay, I probably need to understand Reader to a certain degree, how structures are defined and how the whole thing works, to find a real bulletproof way to match the most important functions. So I was going after quality instead of quantity. And I wanted to have the heap management functions, which is of course very important for root cause analysis, or if you want to dive into exploitation. And I wanted to have as much object information as possible. So what do we want to know about objects in general? First of all, we need to identify them in memory. Like if you had a few slides before our crash, we had the object in ECX. You want to know what that object is to understand maybe what is happening right now. Why does it crash? Where does the crash come from? Then we need to, or what would be good to know is the v-table offsets in the binary that you can identify, or the v-tables for the objects. And it would be handy to have a way to find all the methods and properties which are exposed to JavaScript. And even more important, to find all the entry points for the methods, getters and setters in the binary. And it would also be nice to have all the function names in the vtable. So let's see what we can do. My first attempt was a function which is called getClassTag. This is code from the old Solaris version. And as you can hopefully see, it just takes the object and returns a D word from offset hex 10. And when you look at, for example, the field object constructor in Adobe Reader 9.4.1, you see that it pushes offset hex 86 to offset hex, not offset, it pushes the constant value 86 to object plus 10. So that is obviously our class tag ID. And I was like, okay, that might be a nice way how to identify the objects in memory. And I had a look at it, how it is in Acrobat Reader DC. And for the same object, the field object, you see that the ID is 8E. So it differs, and it also differs for all the other objects. There's also is not shifted or pattern that you can say, okay, this object is that. Doesn't work, so that was an obvious fail. You can't use class tags because they're not constant across versions. So my second attempt was doing the whole thing of the type method. I found it at vtable offset plus hex 8 of each XFA object. And what it does is really simple. It just returns a static ID. In this case, for the field object, it returns the static value hex 7C46. And having a look at the same thing in Acrobat Reader DC, we see, okay, the ID is the same. It's also 7C46 for the field object. And I was having a look at different objects, and it really seemed to be constant. So that was a win. We can indeed use the type IDs to identify all the objects that we have. So how do we go about it? It's a real simple pattern. It's always like move constant to EAX and return. And that gives you a binary pattern that you can just search through with either Python script through the whole binary. And by that, first of all, extracting the IDs, matching between ID and object from the old Solaris version, and then finding the patterns in the new acroform.api module gives you all the objects that you have, and that is pretty nice. And it gives you the vtable offsets in the binary as a bonus, because if you find the type method, it always has one cross-reference, and the cross-reference of course points into the vtable, and this offset -8 gives you the entry point or the starting point of the vtable. So with that method you can safely identify 334 objects within acroform.api, and that's not too bad. So we can now identify objects in memory, and we also have the vtable offsets within our binary. So let's have a look at methods and properties. For methods and properties, I found the getScriptTable function, which is located at each XFA object vtable at offset hex 34. And it's also very simple. It just returns a pointer to the data section in acroform.api. And it references the so-called MoScriptTable structure. This structure contains information about all the method names, about the entry points, about the getters and setters, and also the entry points for those getters and setters. And that is very handy, as we can see. So just want to explain the structure a little bit. First of all, we get for a certain object the MoScriptTable pointer, which points into the data section, and it points to a structure which in the first keyword references another MoScriptTable, but in this case it's the XFA container implementation MoScriptTable. That's the parent class of the field object that we have here as an example. And with that you get a class hierarchy as well. So you first have the field object, then you have the container object, then you have the node implementation object. You just have to follow the first keyword and you get the full hierarchy of objects, which is field, container, node, tree, and in the end you have object. And when the first keyword is 0, that means the object hierarchy is complete. And what you also see in the most script tables that we have property and method tables. How do they look like? So the property table is just an array, a zero-terminated array containing pointers to property structures. And the property structures are also very simple. Contains in the first keyword a pointer to the name of the property, and it also contains the function pointer, the setter, and the getter. And for the method table, it's exactly the same. It also contains, or is an array which is zero-terminated, which contains pointers to smaller structures even, which contain pointer to the method name, and the function pointer to the native implementation as well. So the structure is very easy to parse again. So I wrote an idle Python script for that, which parses all the most script table information for all the objects that we found before, and that gives you quite a complete picture of all the objects in the binary and where the getter and setter functions are located. That's very handy if you want to do analysis because you get a little bit of context. So with that, we know the methods and properties exposed to JavaScript, and we have the offsets of the entry points for methods, properties, getters, and setters as well. Something which is still missing, actually I wanted to work on it between Sebastian and Infiltrate, but I was busy with the zero-day exploit, so I couldn't pursue this much more. This is still to do. It would be very handy to have all the function end of the vtable entries, because XFA is very object-oriented, of course, and you find a massive amount of vtable calls, virtual function calls that you can't resolve, and it's very difficult to analyze that. It would be nice to have, okay, we see call edx plus dc, and then we know, okay, this is method so and so. All right, on to the JF Cache Manager, our custom allocator and acro from that API. It's a very simple LIFO-style heap manager, which stores the small data buffers in bigger heap chunks, just like Gmalloc, for example, from Firefox, if you know it, or the acro cache that has been introduced by Hafei Li, I think, 2 or 3 years ago in a talk at Black Hat. And with all those, or like all the other allocators that are specialized for a certain product, they're getting introduced for performance reasons. And the fun thing about it is they are built totally without security in mind, maybe because it's built for performance reasons, I guess. And that's nice for us. We don't have something like heap isolation, what we have in the newer versions of Flash or in IE for quite some time now. And we also don't have technologies like anti-UAF protection, the old memprotect or the new memGC. All that kind of stuff is not present, and that is of course nice for us, as we will see in a second. Short disclaimer, in the next slides I will dive a little bit deeper into the JF Cache Manager, but I can't cover all the details, otherwise it's going to be a 3-hour talk or so. So I will just cover the details which are really relevant for the exploitation process later on. And yeah, more details will be covered in a paper that I will release as soon as I find time, in 2 or 3 weeks or so. So first of all, let's have a look at a very simplified version of the JF Cache Manager. You always have certain allocator structures like the JF Cache Manager, of course, which manages JF memory cache lists, and in these lists we have JF memory caches. These are the most basic structures which manage the big chunks, which are the big containers where our small data blocks are stored in. And we always have a chunk for a certain size X. And the objects and strings, for example, the small data blocks are stored in this chunk. And it's important to know that for a different size Y, we have a different chunk, and the objects of this size Y are being placed into the other chunk. So let's have a look at the storage of allocations of sizes smaller than 100. The JF Cache Manager handles allocations for sizes bigger than 100, hex 100, differently. I will only cover now for sizes smaller than hex 100 because it just explains the basic structures and how they stick together. The rest will be explained in the paper. So we see now, this is the JF Cache Manager structure. At the beginning at offset 0 we have a V table. At offset H we have a pointer to all these structures that handle the allocations for sizes bigger than hex 100. And at offset hex 18 there's an array of hex 100 entries that handle the JF memory cache lists for certain sizes. So if you have allocations of various sizes, they are handled by different JF memory cache lists. What do you see here? And as the name already implies, these are lists, these are arrays that store pointers to the JF memory cache structures. The JF memory cache structure, as you see already here, it's marked red. This is a very important structure because it manages the actual allocations and frees within the chunks, and that is something that will be important during the exploitation process. So for each JF memory cache structure, we always have one chunk where our data buffers are stored in. And as I said, the JF memory cache and the chunks, this will be relevant for the exploitation part. But this is just a general overview of the whole allocator. I can't dive too deep into it. So we've been talking about chunks for quite a while now. They have a certain size, and the size is computed by a simple formula. You always have it dependent on the size. So if you have the allocation size hex 64 in this case, these chunks, these blocks, they will be stored in a chunk of size hex CB20. So when you get a crash and you see, hey, my object is located in a chunk of size hex CB20, can you directly say, okay, then my object will be probably size hex 64, right? Unfortunately, this is not the case. This is because the JF memory cache lists, they can manage blocks of multiple sizes, which means that blocks of two different sizes, X and Y, they both can end up in a chunk Z. So this is exactly the same, the case when or start differently, the allocation X will be placed in the same chunk as the allocation of size Y. If an allocation of a size Y bigger than X has occurred before, and if the size X is in the same range as size Y. And these ranges always follow powers of 2, so you get ranges from 20 to 3F, from 40 to 7F, 80 to FF, and so on. These are the ranges. So in other words, the allocator just checks, okay, we have an allocation of a certain size. Do we have another chunk where blocks are stored that have a bigger size as the allocation that happens right now? And if this is the case, don't allocate a new JF memory cache, a new chunk, just place it in there. This is maybe still a little bit hard to imagine. That's why pictures are always good to have. In this case, we have two allocations of size hex 64, of an object and a string, both of length hex 64, and they're both stored in one chunk, obviously. So when now an allocation happens of hex 48, then the allocator sees, oh, okay, hex 48 is in the same range as hex 64, and we have some space left in this chunk, so let's just place the object in the same chunk. So the JF memory cache list pointer that you have for size 48, that one here is going to be the same as this pointer. They will both point to this JF memory cache list. Let's take a look at the structures within the chunks and what happens when we allocate and free blocks in this chunk. So on the left you see the JF memory cache structure, and on the right you see the chunk. And this special example is the initial state when a JF memory cache structure is freshly allocated for new allocations, and in this example for block size hex 10. So the first field is the block size, in this case hex 10 as I said. We have a max entries entry in the structure, which says how many allocations can be placed into the chunk. Of course we need a pointer to our chunk, in this case a pointer to a pointer. And two very important fields, which are the allocation count, which is of course always checked against the max entries, and the next alloc pointer. This is the most important field in here, which points to a list head, and then you have a single linked list. A single linked list of flinks, forward links, which link together all the free blocks in the chunk. You don't have links, no backward links, only single linked list. So what happens when we allocate the first block in this chunk? What happens is that the next alloc pointer will point to the next flink, so it is overwritten with the flink that we had before up here, and it just moves one flink further down, so to speak. And the flink that we had is overwritten with a JF memory cache pointer, so it points back to the structure here. And of course the alloc counter is increased to 1. So with the next allocation in this chunk, the exact same thing happens. The next alloc pointer is updated, the flink is overwritten with the JF memory cache pointer, the alloc count is increased to 2, and with the third allocation the same thing happens. So the mechanism is actually very simple. The next alloc pointer just moves down in the chunk, and now what happens if we free the second block in this example, this one here? And the next alloc pointer is overwritten with the block address -4, and the JF memory cache pointer that pointed over here before is overwritten with the next alloc pointer, and that's how it completes the single linked list. So that is basically how the allocations and frees work with the chunks. Pretty simple mechanism actually. Might be that you still don't really like the JF Cache Manager and you really want to have page heap back. That is also possible, and you can switch it off permanently. In one of the scripts that I'm going to release, it will find an offset called JF Cache Manager Active, and just find this byte in the data section, switch it from 1 to 0, save the binary, throw the old binary away, and place the new one there, and you've switched off JF Cache Manager permanently. So that might also be handy for fuzzing runs. If you want to do crash triaging, it's always good to have a backtrace where the offending allocation comes from. That is very nice to have. All right, let's have a look at how we can exploit this thing. In my opinion, we always need 3 things when we want to exploit something. First of all, we need to understand the bug. So we've done quite some work there. With the knowledge that we have about the objects and everything, we actually get an idea what is happening, and that helps you to understand the vulnerability itself. And we need to understand the heap, and we've had a look at the JF Cache Manager now, and know it to some extent, and so we can put a check there. And the third thing is you need to know where your corruption targets are and what you can corrupt to reach your ultimate goal, which is bypassing ASLR, because obviously Adobe Reader is a full ASLR target. And what we want to have is we want to find a flexible override target to cause a memory leak. And I would like to have it really flexible so that we do not rely on the perfect vulnerability, that you have a write what where and you can exactly specify what you override. And that's of course always an easy win. But it's always good to have a method which is flexible and which can be used with many vulnerabilities. So I wanted to find a technique which is fast, which is reliable, and most importantly, because it just saves you work, it should be independent from OS and the Adobe or Acrobat Reader version. With OS, I mean, of course, the different Windows versions. I didn't cover Mac OS X or something like that. So what we want to attack is the metadata contained in the chunks, because it's a nice override target, as you will see. So we have two possibilities. With the example that we had before, with the second block in this chunk, which is freed, we can override two things. Either we can override the flink. This is the case where the block is free, and we trigger our exploit mechanism when this block is allocated. Or we hit the JF memory cache pointer in the case that the block is allocated, and we trigger the exploit mechanism when the block is freed. So I can tell you that both techniques are nice for exploitation, but the far easier way is to hit the flink, and that's what we're going to do in the next slides. So the initial situation again with fresh chunk being allocated and all the flinks. Let's target the first flink in our chunk. So this is our override target. Now what we want to achieve is that due to the override, it points to attacker controlled data afterwards. This is of course a requirement, but it's still very flexible actually with every kind of memory corruption, every kind of vulnerability where you can write something, you can override a flink and make it point to your own data. That's not hard. So we override the flink, it points to our data. Now what happens when we allocate the bad block? Then the next alloc pointer is moved down to the attacker controlled data. So it is overwritten with the bad flink. And the flink is overwritten with the pointer back to the JF memory cache we had before. And now what happens with the next allocation of an object of size x10? But then the object is placed directly into our data, and that's exactly what we want to have. That is the perfect situation, because if you have the object in your controlled data, you also have the V table there. You can just read it out and have fun with it. So that's win. As soon as you have the V table in your own data, you have bypassed ASLR basically, and you can choose whatever you want. You can have arrays, float arrays, for example, as your landing zone for the object, or you can use strings, whatever you want. It's very flexible. The nice thing with float arrays is that you can directly override the V-table pointer after it has been placed into your data. It's very nice. And I will use this technique with the zero day that I'm going to show in a few minutes. So, yeah, if you have that situation, your object is being placed in your control data, that is game over. So let's have a look at a practical example. So the setting could be a 0D word, write primitive to an arbitrary address. But I will not cover this today. This has been covered during syscan as an example. Wait, let's make it a little bit harder than this one here. And I found a vulnerability that I sent in to ZDI in January. That was actually the first vulnerability that gave me a write possibility, so I thought, okay, that might be a nice one actually for Pwning to own, but it turned out that it was not a beautiful vulnerability at all, as we will see. It's obvious that I can't reveal any information about the vulnerability itself, sorry about that, but we can still describe the exploitation methodology and mechanisms behind it. At least the basic steps, so you get an idea of what happens there. Yeah, short disclaimer, the bug is really ugly. It's really not nice. But I chose this example because it's just a great example of the flexibility of this exploitation technique, and it showcases how flexible this is. Even with bad vulnerabilities, you can still exploit it pretty reliably. So our setting is a write primitive of an object pointer, which is non-controlled, of course, and the object is also not located in the XFA word, but it's located on the OS heap. We write an object pointer to an arbitrary address. This doesn't sound too bad in the first place, but there is a problem. We can only write to an address where we have a 0D word. And that makes it a lot harder because that reduces the amount of addresses where we can write to. My first thought was actually, why not write it to an uninitialized field within an object where you normally have a string, but it's not assigned yet, and then you immediately get a leak. Unfortunately, I did not find that situation. But that would be something very elegant to solve that situation. But I didn't have that in that case. So it's just compare ECX against 0. ECX is under our control. And if at ECX we have something which is different from 0, it just jumps out and doesn't do anything. Otherwise, it will write a pointer to an object there which is being allocated. So my plan was to bypass ASLR by only triggering the vuln twice. And that is actually something that you have to do because the vulnerability is not only kind of uncomfortable, right? But the vulnerability itself is also very, you have to allocate a huge amount of pages that you will see. And you need timeouts, it's a little bit timing based. So triggering it the second time is already a little bit not 100% stable, and triggering it 3 times wouldn't work at all. So my plan was with the first shot, with the first write, to derive information about the heap layout, just to give you some orientation where you are. And the second shot should be the one which is supposed to attack the flink and to bypass ASLR. The first part is very easy. Just spray floating point arrays. It's a better target than spraying strings because obviously you don't have 0D words there. Just push this floating point value, and after spec IEEE 754, it will have a binary representation on the heap of 1337, 1337, and then the 0D word, and it is continuously the same. So you get a pattern on the heap where you exactly know where you have a 0D word and you can override it with your pointer. So that is arbitrarily chosen. The first shot goes to address 10101014, and it's easily reachable with an array heap spray that takes half a second or so, and you have a predictable pattern on the heap so that you can very reliably shoot the object pointer to a 0D word. So after the first shot, it will look like that. AADD, CCDD, just the example here for the object pointer. And as soon as you have the override, where you can search through your arrays, where did my float value change? And you get an offset in your array. And then you immediately have the base address of this array. And the nice thing is, you have a continuous spray of arrays. You also get the base addresses of all the surrounding arrays as well. So after the first step, we now have to override a flink. And flink is an address, obviously not 0. So it is not straightforward to override it. The solution for that is that we can still do a partial override. So the idea behind this, let's manipulate the flink so that it is shifted into a neighboring float array. Just hit the flink, do the allocations, and your object is going to be placed in your floating point array right beside your target array. So that's the plan, but how do I know where my flinks are in memory? And how do I know where I can find this exact flink that ends on zeros that I can override? But there's a methodology behind it. First, in general, if you free one of those arrays, just throw it away, and you allocate objects on the JF cache. Of course, the block size has to be, as I said before, the block size always has a certain chunk size, and you need to spray arrays that match this chunk size for a certain block size. So if you allocate enough objects on the JF cache, at some point a huge chunk will be allocated, and if the size matches, it will be placed exactly at the position where the array was. So you get this picture here. We know the base address of this array, and so we also know the addresses of the flinks, right? So in this case of array Z, we know where the flinks are located. The cool thing is that we also know where, hypothetically, if we freed one of those arrays and replace it with a chunk, we know where all the flinks would be located. So what do you do after your first override? You just scan forward and backward and see, okay, if we free that chunk, there we would have a flink that has 0 bytes at the end. That's exactly the way we search for it. So what we want to have is a flink that has a certain pattern. And the pattern should be XX, YY, and then 4 zeros. So why not only 0, 0? Because if you only override 1 byte, it will not be enough to shift it into the next array. It will just be not enough. Like if you shifted 20 bytes, you don't win anything on it. Or why not 0, 0, 0, 0, 0? But it's very unlikely to find such a flink. So we are really bound to finding a flink which ends on 4 zeros. So if we manage to override this flink, we will have to override it with the upper 16 bits of our object pointer, and the lower 16 bits of the flink will be overridden. So in this example here, we just take the object pointer pointing to the address 09204060, and if we partially override it, you see it down on the bottom, you, in this case, override the 0000 with hex 920, because it's related. So if you partially override this flink, and you shift the flink for 920 bytes, hex in this case, then you have the exact situation that I explained before, that the flink points into your control data, and now you have to just allocate some more objects and wait until your object is located in your controlled data. So that's exactly what will happen if you allocate objects. The vtable will be placed there, and you have effectively bypassed ASLR. How about remote code execution? I actually mentioned that earlier. It's super easy. Just locate the float value, set it to the beginning of your rock chain, and have fun. So that's basically game over. All right, let's have a demo. I hope you can see it. I actually can't see it very well. All right, the demo will have 3 parts. First of all, I will just open our evil PDF and see that we really can execute code. The second part, I will attach a small debugging script, which will just dump some information so that we can follow what happens during the runtime of the exploit. And a third demo which will showcase not this case where we write the object pointer, but where we write the 0D word, the example that I used at Cisco. So let's just open Pocket PDF. Let's see what happens. On the left you see the JavaScript console. It's just for debugging output to see what's going on. And it takes some time, and the reason for that is you see it maybe up here. It has to create a huge number of pages, in this case 411. That has to do with the exploit, is very important. Oh, the exploit seems to have failed, awesome. So let's do it a second time. Yeah. I can also tell you why the exploit is not 100% reliable, but only like 80 to 85%. It's because when we scan for the potential flick to overwrite forward and backward, we might search over a boundary of a heap segment where our arrays are stored in. And you always have this segment header, and it screws up your alignment, and then it doesn't work. But second time is really pretty confident. It's almost like sitting at Pwning. Come on, test it. Okay, what we see now, or not, let me just let me increase it a little bit. All right, we see that we leaked a vtable at 728E6228. Now we can immediately calculate what the base address of acrofrom.api is. And yeah, that's by ASLR, of course. And if I just hit enter now, it's going to execute the shellcode. Obviously, I can't pop calc because the sandbox has a restricted job object. That's not possible. So I have just a lame shellcode which pops a message box which says pwned. But you don't have to believe me that it's executed, but I will show you when we go through the exploitation debugging thing that it really executes the shellcode. quite okay to read? Is the size okay? Okay. So we'll do that. Viewer. To go to the code folder. And start our public. I'll just notice that here, because we haven't muted everyone sees the console well. So, let's see. I could bring the CMD window, of course, to the front, but the exploit is not that stable if you do anything beside it, so it's not, yeah, it's not a nice vulnerability. Okay, that worked, and we execute our code. So let's see what happened in the background, so that you get a little bit of an understanding. Let's revise what we've done before. All right. So first we spray the heap with XEA60 size float arrays, and we shoot at the address that we defined before, 10101004. And we see before we shoot, we have zeros here, and after that we've written our object pointer here. That is stage 1, the initial override to get orientation in the heap. And we can immediately compute the array base that you see here. If you dump the information, you see the usual array header information and the data following afterwards. So then we scan to find the flink that we want to overwrite, and we find it at address 103BFFE8. You see it down here. We have a flink which ends on 4 zeros. That's exactly what we want to have. Now we trigger our bug and we override it. And you see here, this word has been overwritten, and also these 4 bytes over here have been screwed up. So if you just have a look at the bytes, you see as well that this D word here has been written. So then we allocate our objects, and we see, okay, at some point the flink is being replaced by the JF memory cache pointer, which is the one here. And it searches through the float array where the override happened. And we see that at address 103C1A08, we have our override. And if we dump the data in there, let's go down to the bytes here. You see the vtable here. It's 71106228. So you actually have to just search for the lower 16 bits of the vtable. You know them, you can predict them, and that's how you get the vtable pointer. And since we are in a float array, we can just set floats and override them. That's what you see down here. So you have this address, which is the same as this one here, and we override it just with 10101010, because at that address.
I think your mic died.
Mic died?
Yeah, use this mic.
Sorry about that. Okay. So we see that we can just override our object's vtable with 101010, and what we do afterwards is we just place our data there. Because it's again within our array heap spray, we can free one of the arrays, reallocate them with our data, and you see down here at 10101014 you have our ROP entry. Because it executes call EAX +4, and then the ROP chain starts, and then it says trigger RCE, and that's exactly what happens afterwards. This is all about seen with this demo is that it takes quite some time until the exploit actually triggers, but that has only to do with the vulnerability itself, because it has to allocate so many pages, and the bug itself happens during the rendering process, and that's why it takes some time. But I have a second demo here which showcases that the vulnerability or the exploit methodology is actually very, very fast to trigger, especially if you spray strings and reach an override so that your object is placed in your own data. That is very, very fast to do. So the example that I had at Syscan with the 0 DWORD override, that's actually the second demo that I prepared. And you will see that this is very fast, and this actually never failed yet. Let's see how it does this time. Not even 2 seconds, 1.5. And again, we have bypassed ASLR, and that's all about it. So this is only the part of the, okay, of course it crashes afterwards. This is not a polished exploiter, so I just coded it until it bypasses ASLR, and the rest is actually obvious. Go on. Oh, you can do this again. This works fast and very reliable. What I did in the background is just a debugging script which gets a message from your JavaScript, hey, do a 0 DWORD write at a special address, and it's going to do the override. That's actually all the debugging script does. And so you see, this is very easy to do. It's very fast, and it's a very nice technique, actually, also to exploit bad vulnerabilities. So the conclusion is, as I said, it's very easy, a highly effective technique to leak data. Of course, it's no global read-write primitive, but still it's enough to pwn the reader. It's totally version independent. I didn't check versions 9 and 8 and so on, but I'm pretty certain that this will work out of the box without any changes. But I can say that it works for reader 10, 11, and Acrobat Reader DC. So you don't have to code in your exploit, if version is so, do that, and if version is so, do something else. You don't need that. And it's, of course, OS independent. It works on XP, it works on Windows 10. I only showcased it here on Windows 7, but it's very, it's OS independent, as I said. As you've seen with the second example, it can be very fast. So between 1 and 2 seconds should be doable with better ones than the one that I showed you. As I said, the ZDI case is just a bad vulnerability. It's a flexible technique that it can be used with almost every kind of override, as we've seen, even writing a pointer to a place where we have to have a 0 DWORD, even that is exploitable. And as we've seen, a custom allocator proves once again to be a perfect target in memory corruption scenarios. That's always a nice target for us. Thank you for your attention.